We're going to take a look at two more theorems in this video. The first one says if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is parallelogram. This is just the converse of the theorem we knew about quadrilaterals, parallelograms. So again, it's just saying, given a quadrilateral, four sides, if you know that the opposite sides are congruent, then that's enough to know that the parallelogram is, or the quadrilateral is a parallelogram. So again, looking at a proof of this, we're going to use one of those theorems that we learned about in the last video, which says that if opposite sides are congruent and parallel, then if one pair of them, then it's a parallelogram. And so we can do that because we know that AB is congruent to DC, that's given to us, and AD is congruent to BC, right? That's our given because that's what's stated up in our theorem. Opposite sides of a quadrilateral are congruent. Then we just draw in a diagonal. Note, if you're ever not sure what to do on one of these, drawing in a diagonal is a good idea. So we're going to just quickly see that diagonal is congruent to itself by reflexive property, which now we've shown that we've got three sides that are congruent. So by side, 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 triangle ADC is congruent to triangle CBA by side, side, side. So now we've proven these two triangles are congruent. We did that because now I can say that those two angles are congruent. So angle BAC is congruent to angle DCA, and that is by CPCTC, which that then tells us by the converse of alternate interior angles that AB is congruent to CD, not congruent, parallel to CD, because those are alternate interior angles, right? The BAC and DCA, and so if they are congruent, then the lines are parallel. So now we've shown that a pair of sides is parallel and congruent. So that's enough to say that ABCD is a parallelogram. And that is if one pair of opposite sides is congruent and parallel, then it's a parallelogram. That's our reason for showing that ABCD, given opposite sides are congruent, is a parallelogram. Our last theorem here from this section says if both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So again, same idea. You've got this. You're given that angle A is congruent to angle C and angle D is congruent to angle B. And you want to show that this quadrilateral is a parallelogram. This one actually use a totally different method to prove true. And so we say angle A is congruent to angle C and angle B is congruent to angle D. But that was what's given to us. So this one, if you try to draw in a diagonal like we had on the previous problems, you run into issues because you split up these angles and we can't use, like if I draw in AC, I can't use A and C being congruent because we don't know how it splits it up. It doesn't necessarily bisect the angle. So instead, we're not going to use congruent triangles at all. What we're going to recognize is by the triangle angle sum, or the polygon angle sum theorem, measure of angle A plus measure of angle B plus measure of angle C plus measure of angle D equals 180. And that is by the polygon angle sum theorem, not 180, 360. It's a quadrilateral. So the four angles add up to 160. Then I can do some substitutions. First, we need to show that congruent angles means equal measure by definition of congruent angles. And then if we do some substitutions, what I'm going to do is I want to show that A and B add up to 180, because then by converse of same side interior angles, these lines would be parallel. And so we're going to say measure of angle A plus measure of angle B. I'm going to plug in angle A for angle C here, measure of angle A, plug in measure of angle B for measure of angle D. That's just by substitution. I'm going to simplify this, which we call as a substitution step as well, because we're replacing measure of angle A plus measure of angle A with measure of angle 2A, and measure angle, or 2 measure angle A, measure angle B plus measure angle B with 2 measure angle B. And then I divide it out and I get measure of angle A plus measure of angle B equals 180 when I divide through by 2. That's just the division property of equality. Then we can do another substitution, plugging in measure of angle D for B. And the reason I do both of those is now I know that A and B are supplementary. So that means that AB or AD is parallel to BC. And then I also now have shown that A and D are supplementary. So that means that AB is parallel to CD. And that is if same side, or the converse of same side interior angles theorem. And so I just said that I'm able to show that these two are supplementary. So that means those lines are parallel. And then the same thing about A and B. That then is enough to say it's a parallelogram. And that's just by definition. So by definition of a parallelogram. And so what we've done is that we've got now 5 ways of proving something's a parallelogram. We have the definition. That's what I just used in that last step. Definition said opposite sides are parallel. So that's kind of a first, can I show the opposite sides parallel? If I can, that's an easy way to prove that it's a parallelogram. And then I have these other ones we've learned about. We have the opposite angles are congruent. That means it must be a parallelogram. We have the opposite sides are congruent, must be a parallelogram. Diagonals bisect each other, must be a parallelogram. Those all are converses of what we know about parallelograms. The third one, this 6-7 is the one that's a little bit unique, which is, or the 6-6, which is if one pair of opposite sides of a quadrilateral is both congruent and parallel, then the quadrilateral is a parallelogram. That one's a little bit harder to remember just because it's not a converse of the theorems we learned about parallel.